All right, today we're going to dive into what could be a totally new way of thinking about Alzheimer's therapy. It's really groundbreaking stuff. For decades, the entire approach to fighting Alzheimer's has been, well, a bit like a battering ram. We've been trying to force medicine into the brain. But this raises a huge question, one that's changing everything.
Okay, so to really get this new strategy, we first have to talk about what's going wrong. It turns out the problem might not be what we thought it was. It's about a breakdown in the brain's own security detail. It's Gatekeeper. So, at the center of this whole thing is this nasty little protein called amyloid-beta, or A-beta for short. Now, in a healthy brain, your body just clears it out, no problem. But with Alzheimer's, this stuff starts to build up, forming these gross, sticky clumps that are just poison for your brain cells.
And the thing that's supposed to protect the brain from junk like that, it's called the blood-brain barrier, the BBB. You could think of it like the most exclusive nightclub bouncer in the world. It's this super selective wall of cells that decides exactly what gets in, and maybe even more importantly, what gets kicked out.
And here is where it gets really, really interesting. This is a snapshot of that gatekeeper system in a healthy brain versus a brain with Alzheimer's. You can see things going wrong all over the place. It gets leaky, transport breaks down, but look at that very first line. This thing called LRP1, it's cranked up high in a healthy brain, but in the Alzheimer's brain, it's basically gone, vanished. And that, right there, is the key.
So what on earth is LRP1? Well, if the blood-brain barrier is the bouncer, LRP1 is the dedicated exit door for troublemakers. Its whole job is to grab that amyloid-beta junk from inside the brain and literally throw it out into the bloodstream to be hauled away. But in Alzheimer's, that exit door just disappears. It's gone.
So you can see the problem, right? The brain's own cleanup crew is basically off the job. And that led researchers down this long and really frustrating road. For years, pretty much the only strategy was, like I said, brute force. The logic was simple. If the brain can't take out its own trash, then we've just got to force our way in with drugs that can do it for them. We've got to break through that barrier.
And yeah, this is why that whole approach was such a dead end. Turns out the blood-brain barrier, even when it's not working perfectly, is still incredibly good at its job of keeping things out. So most drugs just bounced right off. And a few that kind of squeezed through, they often caused all sorts of side effects. But the biggest problem, the real kicker, is that none of this fixed the root cause, that broken exit door.
And this is where the story takes a huge turn, a total change in perspective. Scientists started thinking, wait a minute, what if we stop trying to fight the brain's security system and instead we try to help it?
Which brings us back to this big game-changing question. Instead of trying to smash through the gate, what if we could just fix the gatekeeper? I mean, it's such a simple idea, but it's a total 180 from everything that came before.
And that's the core of this new idea. The goal isn't just to get rid of the amyloid plaque. The real goal is to fix the system that's supposed to be getting rid of it all along. We're not targeting the trash. We're targeting the broken trash disposal system, that LRP1 pathway.
Okay, so that's a great idea in theory. But how do you actually do that? How do you fix a tiny microscopic system inside the brain? Well, you send in a microscopic mechanic.
And this is it. This is the nanomechanic. It's an incredibly tiny, engineered nanoparticle. Think of it like a heat-seeking missile, but instead of heat, it's designed to hunt down and lock on to those failing LRP1 receptors on the brain's gate. It's a delivery vehicle for a repair kit.
And how it works is it's so clever. Okay, so first, the nanoparticle finds those broken LRP1 receptors and latches on. Then, step 2, it delivers its payload, which is a drug called simvastatin, right into the gatekeeper cells. This drug then goes to work repairing the broken machinery. And finally, with the system fixed, the brain's own cleanup crew gets back to work. Those exit doors swing open and the toxic stuff starts getting cleared out.
All right, so that's the theory. Does it actually work? Well, they tested this out on mice that have an Alzheimer's-like condition, and the results, honestly, they're pretty stunning.
Just look at this comparison. On the left, that's the before. A mouse brain clogged up with all that toxic amyloid plaque, and the mice were having trouble with memory and learning. And on the right, that's after the therapy. You see a huge reduction in that plaque. And even more importantly, the mice actually got better. Their memory and learning abilities started to come back.
And this quote from the study really says it all. The big win wasn't about bypassing the barrier. It was about repairing it. They didn't have to force anything. They just fixed the brain's own natural process and then let it do its job.
So
Let's wrap this up. What's the big picture here? What does all this mean? It's not just a new drug, it's a whole new way of looking at how we might treat diseases like Alzheimer's.
So, to put it all together, the whole game is shifting. We're moving away from the brute force bypass strategy and towards a much smarter repair strategy. The goal now is to get that LRP1 receptor working again. And using these amazing nanoparticles to deliver the medicine right where it needs to go, well, it makes it all possible. This vascular first idea is a really hopeful and, frankly, a much more elegant new direction in the fight against Alzheimer's.